Very good morning to all of you. So today we will try one more simulation, and this simulation is about the open loop and the closed loop buck converter using PSIM software. Now you know that the buck converter, it means that the output voltage will be lower as compared to the input voltage, and this DC-DC converter is going to be operated at a very high switching frequency. So you can see that this is the circuit diagram of the buck converter. Now, if you want to write the equation, or you can say transfer function for this open loop buck converter, it will come as D. D means duty cycle. That is the time for which your switch is on. If you write the formula for D, it will come out to be D will be equal to T1 upon T. That is in terms of decimals. But if you want in the percentage, then you will have to multiply by 100. So that is the case. Now you can see that there is a switch and a diode is there. So the power will always flow from source to the load. Now, if you just replace this diode by the switch, then there will be both the modes can be possible. That is the buck mode and the boost mode. Now, this is the inductor, which is a very crucial component in the DC-DC converter. This inductor value, there is a formula for this inductor. So depending upon the critical value, if you are having a value more than the critical value, then your DC-DC converter is going to be operated in CCM mode. Below the critical value, it is going to be operated in the DCM mode. So we'll check the things in the PSIM software. Now this is the interface of the PSIM. So we'll be taking the components. Okay, just a minute. The components, then a DC source is required because it is a DC-DC converter. Then diode is also very important thing. I think the diode is in the elements. Yes, this is the switch. This is one is the diode. Then you will have to place an inductor that will act as a filter along with the capacitor. Then you just connect the value of resistor also. This is a load. In our case, we have taken a resistive load. So, or you can take any lighting or the heating element, heating load. Okay, so we'll be connecting all the things by a simple wire. So this will be the case. All right, just a minute. Okay, now yes, the filter has been connected along with a load, along with a load. You will have to make strong connection. If you don't make strong connection, then the circuit will remain open only, and in that case, you won't be getting any output voltage. So this is the thing. I think I will have to delete this thing, and in this way, just a minute. Hold on. So this is yes, the circuit has been connected. Now there is a pulse generator. This pulse generator we will have to connect. Okay, so we will keep the duty cycle as 0.5. So okay, the ground has not been connected. Now this DC-DC converter is in the open loop configuration. Okay, now we'll set the values for it. This is 24 volt. We don't want our value to be displayed. Now this is the inductor. So this will be 250 microhenry. So for microhenry, you can take U as U. Then this one is in microfarad. Then again, this is the load resistance. You can take it as 5. Okay. Now you need to find the voltage input and the output voltage waveform. So for that, you have taken a voltage probe. So this is the voltage probe. Just a minute. Okay. We need some differentiation. So for that, please change the name of that. That is the V in. So this is connected. Then we out. Okay, the both the things are over. Now we need a simulation control. Simulation control, this is the thing. Okay, so now everything is properly connected, so we can check the waveforms of it. But before that, the pulse generator, right? Here you keep it as 25 kilohertz. You can see that the complete cycle will be from 0 to 360 degree. If you are keeping it as 0 to 180, it means that there is a duty cycle of zero point 0.5. So zero point 0.5 into 24, you should be able to get 12 volt. I think we will have to place ammeter also, because we are also more interested in checking the inductor current waveform. Okay, just a minute. Okay, you will have to connect the inductor waveform. So for that, you have to place an ammeter. Okay, just a minute. Okay, in this way everything is connected. So we will run the simulation. Okay, or after running this simulation, you can just have a look at the. Okay, you can see that I think it is in the broader version. You can see if you are keeping it as a 24 volt, because of the limitation of number of point, you can see that this is around 12 volt. This is coming around 12 volt if you just trace the graph. Okay, so we will see the current also, that is inductor current. Yes, somewhere, yeah, it is more towards inductor. You need to, just a minute, I think everything should be properly connected. Uh, okay, I need to, yes, yes, I think it is the triangular waveforms are getting. So this is all about the open loop configuration. If you just make it as 12, we will try to see, then or 48 will try to see, or you can say uh, 28, then you should be able to get 14, I think so. Yes, because 28 into zero point 0.5, that is 14 volt only. Okay, we will check the things. This is right. I think it's coming out with 14 volt. You can see that this is a 28 volt, and this is around the 14. It is hovering around the 14 volt. So this is all about the open loop configuration. Now coming towards the um, closed loop configuration. So how it has to be done, we'll be seeing now in a few minutes. Okay. So for that, you need a voltage sensor, because ultimately you have to maintain a constant output voltage. So for that, a voltage sensor will be required. So this will be a voltage sensor. I have taken it from the bottom. Okay, so right. Then you will be requiring a summer also. So this is a summer, because you need to compare the reference value also. How much voltage you want to obtain there? Okay, just a minute. I'll keep it as 24 volt, because this is more realistic. Now the reference value. For the reference value, again, this is the reference value which you have to maintain. Okay, just give a ground to this reference value. Okay, now this will be connected here. Okay, so this is the thing. Just a minute. I need to, elongate this thing. Right. This voltage sensor is connected across the load. This voltage sensor is connected across the load. Okay, this is the thing. Then after that, what you require, because the error will be generated. You can see this as the reference value. Okay, just a minute. I'll keep the probe here, because that will give more, again, a realistic thing. Just a minute. I think everything is connected. This is the reference will do the simulation. The error will be there. Now this error will be fed to the PI controller. So this will be the PI controller. I think everything is, just a minute. We don't want to enter any text here. This is the PI controller. Then error will be, yeah, error will be compensated, and so we'll be using the limiter also. Yes, because we don't want our we don't want we want everything to be in limit. That is the upper limit and the lower limit. Now this will be zero. Lower limit should be zero because we want pulses. We want pulses from 0 to 1. Right. Then this will be connected. Okay. So after that, you need to compare the, this will create a, the constant value, and this constant value will be compared with, this constant value will be compared with the waveform, that is a sawtooth waveform, or you can say a triangular waveform. So again, this will be connected. I don't know about the values which I have set here. Okay, this will be, I think I will take this as the 10. That will be more again. The things are there. Okay, this will be here. Now a triangular waveform, where the triangular volt waveform, you can go for sawtooth waveform also. No issues in that. Okay, just a minute. This will be connected here. Okay, so now I think this is a closed loop, so you don't need any pulse generator. You don't need any pulse generator. So this will be connected here. Where is the yeah, this is the control circuit which we have designed here, and you have to provide the pulses. For that, you require some, isolation, or you can say a gate driver. So this will be connected here only, right? Okay, so now this is the carrier waveform. I think we need to provide a 25 kilohertz. Then this is the peak value, that is V peak to peak. Mm, uh, so I think this will be this what with this waveform. I think you will be getting in both the above the origin or below the origin. We want in this fashion, that is one. Then this should be zero. Right. I think this is what peak to peak. Let us see. Let us have some um, things. Okay, this is 25 kilohertz, zero point 0.5 duty cycle. This we have set as, okay. This is the 20. We need to obtain a 20 voltage at this. Let us check whether we have obtained the results properly or not. This is in the closed loop configuration. What we have done, we have taken a voltage, then we have compared the things, compared the actual voltage with the reference voltage. This is a reference voltage we want to have at the load side. Now in this case, we have taken this as the 20. So 20 volts should be there on the load side. Okay, just we'll check the things. Okay, just a minute. So we are more interested in this only. We are least interested because that is 20. Yeah, you can see here 20 volt is coming. 20 volt is coming properly. Okay, we'll check with the other values also. So how much voltage you want to have at the output? Let us play with the things. That is 18 volt. 18 volt. We will. This is the 18 volt, and we want. You can see here 24 volt. This internally the duty cycle is changing, and accordingly you will be having these things in your screen. You can see here, right? This is obviously right. 18 volt is coming. 18 volt is coming. You will be having some ripples. So that will be that ripple will be filtered by a proper selection of the inductor and the capacitor. In this case, we have taken a rough selection. So you can see that 18 volt is coming. Now we'll check whether the 22 volt is coming or not. I think this is very high because you can say 24 is the input voltage and 22 is duty cycle will be more towards that point 0.8 and point 0.9. I don't know what is the duty cycle, but let us check whether this is sufficient enough or not. Let us check again. Yes, yes, it is coming. Okay, it is coming. There will be, you will have to change the value of P and I. Okay, so now this is about the closed loop of the buck converter. So we have successfully implemented the open loop and the closed loop configuration of a buck converter. So we'll meet in the next video with a new simulation. Thank you. Thanks a lot.